Welcome to my presentation. It's pretty much just about molecular dynamics in the context of Part 1 and Part 2, designing OLEDs with DFT calculations and simulations of alpha protein stretching. Part 1, designing OLEDs with DFT calculations. OLEDs use organic molecules to produce light emission by placing layers of organic molecules between the anode and the cathode. On either side of the emission layer lies a HDL and an ETL. The HDL layer transports positive poles and blocks electrons, while the ETL layer transports electrons and blocks positive poles. You can see how it does this. The HDL layer has a HOMO of energy just below that of the anode, so it can easily transport the positive poles, but it has a LUMO that it's just too high for the electrons to even reach, so it blocks the electrons from getting that far, and vice versa for the ETL layer. And then the electrons are recombined with the positive poles in the emission layer, and photons are emitted. We are given two molecules that could be used for the roles of HDL and ETL. These are CutTMePA and CutTmPyPB. They have cut as a prefix as just a way of shortening the names, but I will refer to them as PA and PB. The question is, how do we find out how applicable these molecules are for the roles of HDL and ETL? The plan of action is to first use ORCA to determine which of the singlet and triplet states are the ground state for both molecules. Then it's to classify between which is suitable for HDL or ETL material. And then it's to determine the ionization and electron affinities. My DFT calculations are as follows. So for PA we have the singlet state, the triplet state, and the lower energy is the singlet state from this, so we know that it's the ground state. Cationic state, energy of the anionic state, and then from this we can work out the ionization energy, which is just the ground state minus the cationic state to get the energy needed to remove an electron, which comes out as minus 139 kilocal per mole. And then the electron affinity, we need to instead subtract the anionic state from the ground state, which gives a value of minus 30 kilocal per mole. And then the HOMO value and the LUMO value is there as well. And for PB, we've got the singlet and triplet states, showing similarly to the PA, that the singlet state is the ground state. And then cationic state, energy of the anionic state, and the ionization energy, electron affinity, and HOMO-LUMO values are right there. For the classification of the materials, the HOMO-LUMO energies for PB are higher than for PA, so PB is suitable for ETL and PA is suitable for HDL. These are the VMD visualizations for the HOMO and LUMO orbitals of PA, and these are the visualizations of the orbitals using VMD for the HOMO and LUMO of PB. And they've got pretty colours. Part 2, simulations of alpha protein stretching. So in part 2 we are investigating a single alpha-helical segment of the 2B part of the vimentin intermediate filament dimer, which is shown below. An alpha helix is generated from the stabilization of H bonds when a single polypeptide chain twists around on itself. So hydrogen bonds actually provide a lot of strength to the protein, and the purpose of a vimentin protein is to provide structural integrity to a cell when undergoing large deformations. The plan of action for part 2 is to first use SMD to analyse the behaviour of the alpha-helical segment under tensile stress. It is then to use VMD to visualise this by using the 2 files made from SMD. To carry out the SMD simulations, we can use the stretch mold tool from NanoHub. And to use this, you first need to upload 3 files into your initial geometry. You have a PDB file, structure file, and a fixed atoms file. Then you need to upload a PDB parameter file. And if you're plotting on the x-axis like now, then you put a 1 in the direction x and 0 in the direction y and z. And then step 3, upload your simulation parameters. And for the sake of this energy plot, it is 5,000 steps. Then to plot along the x-axis with 1,000 steps, you just do the same thing, but you change the number of steps to 1,000. Get a beautiful graph like so. And then to plot along the z-axis, all you do is just go back and change your direction of z to 1 and direction of x and y to 0. An observation made between these 2 energy plots is that the gradient for the z-axis is shallower than for the gradient of the x-axis. And now it's time to use VMD to visualise this simulation. So when you've opened VMD, you first load a new molecule and you load the PSF file from the zip files you downloaded from the SMD. And then you load into the molecule the DCD, the trajectory file from the zip files. And then you can change the graphics of the representations by clicking Graphics, Representations, and to make the helical segment be clearer within the water molecules, select the protein atoms and change the drawing method to New Cartoon. If you want, you can change the colour, but I liked blue and the default was blue. And you can see here the helical segment is clear to the eye within all of these water molecules. Now this is the 5,000 step simulation along the x-axis. You can see that the structure of the protein is maintained once the force is applied. So these hydrogen bonds really do work. They keep the structure together. They provide structural integrity. Now this is just the same as the one before, but it's a simulation with 10,000 steps instead. You can see the protein being stretched sort of easier this way. This is again a 10,000 step simulation, but it's along the z-axis instead of the x-axis. A question that was asked was what's happening with the water molecules in the simulation. And you can see that the water molecules sort of cluster behind, they're sort of left behind as the protein is being stretched. So I thought, well, the force pulls the protein segment and its H bonds persist, so are pulled with it. But the other water molecules are left behind because the dipole interactions they offer are too weak against the force. They break away. Thank you for watching.